Hello. The goal of this module is to expand our understanding of the mass, energy, and entropy balance equations we developed in the last modules by applying those to a very simplified system. So let's begin by looking at different types of systems. So this is an animation from the states section, states, systems classified. And this particular system is called open, unsteady, non-uniform system, the generic system based on which we developed our equations. Well, so let's go over this different kind of system. The first, open versus closed, is very simple to understand, but it's important to remember. So you go over the boundary and look if there's any mass transfer anywhere. If the answer is yes, it's open system. And if you're sure that there is no possibility of any mass transfer, it's a closed system. So it's a kind of an obvious definition. The unsteady versus steady, to understand that, what you do is to pick a local system anywhere you want. And if you find that the local system, the state of the local system is not changing with time, then it will be a steady system. So it has to be true for any given point. So in other words, in this particular case, as you can see, the color inside is changing, and the colors inside really represent properties that describe the local equilibrium. So if the colors are changing at a given point, you can say it's an unsteady system, whereas if it's a steady system, you'll notice that at any given point, the colors are frozen. They're not changing with time. A practical example could be a block of copper you're heating. So if it is getting hotter and hotter, if you take a picture, it will be an unsteady system because the picture will be changing with time. To understand what is a non-uniform versus uniform system, you take, let's say, two different local systems anywhere in your system, and you will notice that in case if the system is non-uniform, then if the system is non-uniform, then the two states may be different. Whereas if it's uniform, that means two states at any two different locations have the same state. Two local systems at different location in the systems have the same state. That means it's uniform everywhere. So if I have a block of copper, temperatures everywhere is equal at a given time. Of course, if it's unsteady, as you can see, with time things can change. So our task will be this time, what we'll be focusing on is a closed system and that is steady. So we'll limit all our discussion to this specific type of system in this particular module. Okay, now that we understand what is a closed steady system, let's go and go over. So we have covered what is an open steady system. Let's jump into different mechanisms of entropy generation before we go and try to understand what is a reversible system. So again, we're going to go through a bunch of animations here. So I want to go over a few cases. Please ignore all the equations here, where I want for you to intuitively see how friction, different types of friction, generates entropy. This is the picture of a gearbox. Let's imagine these are gears turning. Work is coming in, shaft work, going out at shaft work. And in this gearbox, what is going on is that there could be friction inside. So this is easy to understand, mechanical friction. What friction wants to do? It wants to stop relative motion of the gears. So wherever you find the nature is trying to destroy a difference, entropy is created. So entropy is created inside because of mechanical friction. Probably the gearbox is going to get warmer, and the gearbox, the surface could be a little bit hotter than atmosphere. Then heat will flow from the high temperature to low temperature, and that is trying to destroy the temperature difference. So there will be some entropy generation on the sides, or on this external zone. Let me just try to draw that. So there is all this kind of entropy generation here because of friction, and because heat is leaving, so there could be entropy generation in this area also, right, where the temperature drops. So these are called internal generation and external generation. We'll come back to that. Let's keep looking at different things here. Also, let me just define quickly, in this particular gearbox, you can say the desired output is how much shaft work is coming out, and the required input is how much work is going in. And their ratio is called the first law efficiency, or the energetic efficiency. That's a general definition of energetic efficiency. So as we see different picture, we'll come up with definition of device-specific energetic efficiency. Okay, so let's move on. Let's look at another system. In this case, well, this is just a hot reservoir here, very high temperature, and this is a cold reservoir on this side, and there is some kind of a wall, and the heat is flowing from left to right. As you can understand, heat entropy will be generated wherever the temperature difference is getting destroyed. Nature is trying to equalize the temperature, and as a result, it's like an entropy making machine. So I would let you go through the rest of the animation without spending all the time here, but I'll just quickly browse through them. This is another case where you can identify where friction is generated, because here there is a lot of, this is a pedal wheel, so the air inside, or the fluid inside, is moving, and there is viscous friction creating entropy inside. The heat transfer is causing entropy generation outside the system. Here there is some electrical friction because there's an electrical wear. In this case, two different fluids are mixing, and during mixing there is friction. It's called mixing friction. So there are different types of entropy generation that I'm trying to show you here. This is another case where this is called free expansion. This is another fundamental way in which entropy is generated. In this case, there's a chemical reaction in addition to mixing, and as you can understand, the difference not only between the concentration but something called chemical potential is reduced by a chemical reaction. As a result, lots of entropy is generated. But an important thing here to understand is that entropy can be generated inside a system, inside the physical boundary of the system where the fluid is, or in its immediate surroundings. And we'll call it internal versus external. So what I mean here is that this is again going back to our generic system. The black boundary inside is the internal system. So the internal system is the black boundary. So all the friction inside that black boundary is called S dot gen internal. Whereas there could be entropy generation right outside because of heat transfer, etc., and that will be called S dot external, S dot gen external, as shown here. So if we the red boundary, on the other hand, encompasses all possible friction, all possible thermodynamic friction anywhere because of this system, and it's called the system's universe. So if we want to know the footprint of any natural action, natural processes in a system, we better look at the system's universe. So one reason why entropy generation is so important, because it's kind of like a footprint, like a finger mark of a natural process. If heat is trying to destroy a temperature difference, or friction, physical friction, is trying to destroy a velocity difference, this phenomena produces entropy. Entropy is generated, and once generated, entropy can never be destroyed. That's the second law of thermodynamics, right? There cannot be negative friction. So entropy generation, in another way to look at, is the fingerprint of a natural process. You can never undo it once it's generated. So you cannot undo a process if entropy is generated. So if entropy is not generated, suppose we do something in a manner without causing any friction, in that case, the system is called reversible. Well, there are a few shades of definitions here. If there is no friction inside the internal boundary, then the system is said to be internally reversible. So here is a internally reversible system. So there is no friction inside, but there could be friction outside. What is externally reversible means there can be friction inside, but not outside. And when you say reversible, that means there is no entropy generation anywhere. So that's an ideal situation. A reversible system means there is no entropy generated inside the system or in the immediate vicinity of the system. We can reverse whatever is going on without leaving any footprint. And that's the idea of entropy generation versus a different kind of system based on entropy generation. Okay, so now that we have covered what is kind of the internal external boundary of the system, what is reversibility, and even energetic efficiency, which we call the desired output versus required input. So let's formally define the first law efficiency or energetic efficiency. This is called eta. One means first law is the desired energy output. Any efficiency is desired divided by required. So desired energy output, required energy input. So based on device, this definition will change. We'll keep that in our background so that we can quickly define the energetic efficiency of a given device. Okay, now it's time for us to go and simplify the governing equations for our closed steady systems. So we go back to animations, closed steady systems, and let's start from the beginning of this animation that defines the system here. So as you can see, it's a closed system. There is no mass going in. Inlet I and E are blocked. And the system is steady, as we discussed earlier. That's because the picture of the system is not changing with time. Think of what is the consequence of that for a second. For instance, so if somebody asks you that find the mass of the working fluid in the system, well, think of the air in your room. Suppose the room is the system. Then to find the mass of the air in the room, you may have to divide the entire room into small systems because the temperature and pressure could be different, technically speaking, from point to point in a system. So you have to sum up all this mass of each of this local system, which I call pixels, easy to understand. So you have to sum up all the pixels together to get the total mass. Similarly, to find the total energy of the system, you have to find the energy of the local system and then sum up all this energy together to get the total energy of the system. Same with total entropy. But one thing for sure, that once you calculate the mass, energy, and entropy of the system, as time passes, things will not change because the picture hasn't changed. Every pixel behaves, they have the same color as time passes by. So that's the beauty of a steady systems, that none of the total properties change over time. Okay, with that in mind, let's go see how the animation simplifies our governing equation. So we move forward. So these are the governing equations that we developed for mass, energy, and entropy. They are applicable to any kind of system. So first, we recognize that there is no mass coming in or going out, so the mass terms drop out. That's a considerable simplification. And then we also recognize that if mass, energy, and entropy doesn't change with time, then mass, of course, is constant, and the EDT and DSDT drop out because that's what the derivative means, how energy and entropy changes with time. If they're constant, so they are zero, and that's what leads us to the final set of equations, which are very simple. So every time we want to analyze a closed steady system we'll begin with this equation: mass equals constant, energy equations becomes simple like this, and entropy equations becomes like that. One thing to remember, that this q dot and w dot external, they're algebraic in nature. So q dot and w dot external are governed by the Wien-Hip sign convention. In other words, based on a particular situation, we have to recall that using Wien-Hip, we have to algebraically substitute the value of q dot. So for instance, if a system is losing 5 kilowatt heat at the rate of 5 kilowatt, we'll substitute -5 for q dot. If a shaft work is coming into the system, work in is negative, so we'll substitute negative number there. On the other hand, S dot gen has to be always greater than or equal to 0. It can never be negative. It's 0 when the system is reversible. Okay, so let's quickly see if we can develop the governing equation for specific closed steady system, particular systems. This would be a good example. So this is a light bulb, electric lamp. And what does an electric lamp do? It's an incandescent bulb. These days, most bulbs are LED lamps, but in the olden days, even now you can find some electric lamp of incandescent type. A lot of power goes in, work is going in as electrical work, and the bulb gets hot, so energy comes out through light and heat. In case of LED lamp, most of the energy comes out in the form of light. In case of incandescent lamp, a lot of heat comes out. A lot of heat comes out, but light is also a form of heat. It's radiation, radiative heat. So the energy that is coming out in the form is q dot out in this case, and one energy that is going in is w dot in. Why we are not calling them external or q dot here, or external work or w dot external or q dot? Because these are absolute values. W dot in, suppose we have a 1 kilowatt lamp, then W dot in is just 1 kilowatt, because the direction of the transfer is clear from the subscript. On the other hand, similarly, Q dot out is telling us that heat is leaving the system. On the other hand, when we want to substitute that in the energy equation, Q dot, notice we are writing negative Q dot out, and W dot external, we are writing negative W dot in. So this is something to really understand, because a lot of time students make mistake on this particular concept. So a little algebra brings us that Q dot in and Q dot out is same as W dot in, which is kind of obvious in this case. So let's see how the entropy equation will look like in this particular case. Again, the entropy equation, the dt goes to 0, as we explained already. And we are substituting, instead of Q dot, we are substituting negative Q dot, right? Negative Q dot out. So that's like a number. Say suppose 1 kilowatt of electricity was coming in, 1 kilowatt of heat must be leaving in case of steady state. So this will become -1 in this case. And the temperature of the boundary, which is, as you can see, it's an external boundary, which means we are capturing all sorts of entropy generation. As a result, the entropy generation of the universe is captured as Q dot out over T0, which is W dot in over T0. So I would say solve a few problems involving this concept and see if you can capture the entropy generation in the system's universe for a closed steady system. There are plenty of problems in the book, and also there are more animations. I'm not going over each of them. This is a water heater which is at steady state. Basically, again, electricity is coming in, and the water heater, well, the animation is showing an unsteady first and then steady system. In the beginning, the system is changing with time. This is another closed steady system, heat passing through a wall, and is being analyzed here. So I would say I'll stop here and solve a couple of problems so that this concept gets more solid.